Hi, welcome back to the channel. So this is going to be the first video under the series where we look at the topic numerical differentiation. Okay, so this is just more like an introduction video, and what I'm going to do is I want to talk about something called um, data symmetry. Okay, something called data symmetry. Okay, so more like you say symmetric data. So when we say symmetric data, it means that for the point um, x sub I, okay, x sub I where you want to compute the derivative, either it's the first derivative as f prime of x sub I, or it's the second derivative f prime prime of x sub I. Um, you want to like at that point where you want to compute your derivative, there are equally spaced data points on both sides of xi. What does this mean? This means that if I'm to draw this in terms of, let me just try to put up a line to represent a number line also. Okay, so let's say we have our x sub I at this point, and let me say we have another point here and another point here. Okay, another point right here. So let me put this as my x beta, x sub beta, then x sub alpha there. Okay, so when we say there are equally spaced data points on both sides of xi, meaning on the left side as well as the right side. So what this means is that the distance that is here, okay, as well as the distance that is here are equal. Okay, and that distance is the one that we describe as h. Okay, so let me show you this example. Okay, let me show you this example. What this means is that if if you want to compute, I'm going to give you two scenarios. If you want to compute f prime of x sub I, okay, you need to have more like f of x sub I minus 1 and f of x sub I plus 1 at an equal distance. Okay, at an equal distance that is described as what? As h. Okay, this is just some form of a distance, and it's the same thing that I was just trying to illustrate regarding the number line. They need to be at an equal distance. So it simply means if you have your x sub I here, when I had to put my x sub alpha, it's more like this point is what is my x sub I plus 1. Then at this point, if I have x sub beta here, this would be like x sub I minus 1. It's the same thing that I was trying to demonstrate using a number line. Okay, so what about the second derivative? If you're trying to compute the second derivative, f prime prime of x sub I, okay, you typically need you need to have your x sub I minus 1 as well as your f of x sub I itself and your f of x sub I here minus, that would be actually plus 1 now. This is what you need to have. So when it comes to the first point where we say this and that are supposed to be at an equal distance h, let me show you this example that has some data points that we can try to refer to. Okay, so this is the worksheet that we are going to use. There are a several of interesting questions. We have like about 4 questions that we are going to look at. There will be videos on each and every one of them. So just make sure to say you subscribe, ring the notification bell so that when I upload these videos, you'll not be able to miss out on anything. Okay, so we have these data points here. Okay, so we are starting from 0.2 to 1. Okay, we are starting from 0.2 to 1. So the h that I was talking about is the distance from, like the distance from 0.2 to 4, from 0.4 to 0.6, from 0.6 to 0.8, from 0.8 to 1.0. And when you do the subtraction there, when you do the math, this is just going to be something like this. Let me just try to work it out. So what is supposed to be is that the distance between these two, these two, these two, and these two, this is supposed to be equal. Okay, it's supposed to be the same. If they are the same, that's where the issue of symmetry comes about. Okay, that's where the issue of symmetry comes about. So this means that your h is simply equals to, I can say it is 0.4 minus 0.2, which is also the same as 0.6 minus 0.4, which is also the same as 0.8 minus 0.6, which is also the same as 0. Do we have another one? Yeah, we have a 1. So that would be 1.0 minus 0.8, which is actually 0.0.2. There is the same. You have 0.2 here, you have 0.2 here, you have 0.2 here, you have 0.2 here, which is exactly what I was looking for, because I had to ensure to say that distance is equal amongst the data points that I have. So that's what symmetry talks about. Okay, so what about when it comes to, like, when you think of it in terms of when you think of it in terms of the key requirements for symmetric formulas, okay, of which in this case you are talking about the central difference formulas. What are the key requirements? Okay, and of course at this point is where now you start thinking about the formulas and the like. So the key requirements for symmetric formulas is that the first one the first one is that the data the data must be evenly spaced. Okay, you have to ensure that it's evenly spaced, which is what we have observed. The fact that our h is the same throughout is 0.2, that tells us that our data is evenly spaced. Okay, what about the second part? The second part is also kind of like one of my favorite part. It's interesting, and when you just come to think of it, it's pretty actually. You need to have that the point x sub I, it must not be at the boundaries. Okay, that is a very very important point when using the central difference formulas. It's that your x sub I, or whatever value that it is at that point, is not supposed to be at the boundary. Let's look at this from the data that we have. Look at the question. The question is saying, one of the questions is saying, use all appropriate formulas to approximate f prime of 0.4 and f prime prime of 0.4. What are we looking for? We are trying to approximate 0.4. This is basically what you're trying to do. And where is our 0.4? Our 0.4 is at this point. What does it mean when we say it should not be at the boundaries? So the boundaries of this data set is 0.2 as well as 1.0. So we can't use the central difference formulas to approximate this one as well as this one, but we can use those formulas to approximate this one as well as this one. Of course, we have already observed the question is asking us to approximate 0.4 as well as 0.6, but we can also try, just for the sake of practice, to approximate what? This one here, which is 0.8. Why? Because it's not at the boundaries, which is something very important that you have to keep in mind. Okay, so now let me talk about the general guidelines for choosing formulas. Okay, I've talked a little bit about the central difference. What about the general guideline for choosing formulas when you're given a question? Okay, so here's what you do. I'm going to talk about both for the first derivative as well as the second derivative. For the first derivative, f prime of x, there is when you are going to use the central difference. Okay, central difference. When do you use the central difference formula? Okay, use the central difference formula for interior points. Okay, interior points, which is exactly what we are from talking about, to say it's not supposed to be at the boundary. It's the values or the coordinates, like the values in your data set that are on the inside part, not on the boundaries. We have already demonstrated that. Why are we doing this? This ensures high accuracy. Okay, this ensures high accuracy in terms of our approximation. Okay, so it ensures high accuracy with symmetric data, and of course our data is symmetric. Okay, what about there's another formula we call the 3-point endpoint. When does this come into play? Okay, so the 3-point endpoint formula is used at the boundaries. Okay, at the boundaries. So this is what we'll do. Like for 0.2, which is 0.2 as well as 1.0, we are okay using the 3-point endpoint. What about the 5 point 5 point midpoint? Okay, 5 point midpoint, more like a central difference. So for this one, we use it for high accuracy, but the condition, like the tag on this one, is that you have to have a lot of data. Okay, you have to have a lot of data that is available. What do I mean? There are times whereby you write your formula, you try to perform some evaluation, like you try to break things down. If you look at this, the what you're supposed to substitute, if you end up with something like f of 0.2, what you substitute with is this value right here. So you find that the nature of the 5 point midpoint formula is that there are times whereby, based on this same data that I have, after performing some substitutions, I end up with something like, let's say, f of 0. And if you observe here, I don't have f of 0. Or let's say you end up with something like f of 1.2. You don't have 1.2. The highest value that you have is a 1. Okay, so that one works. It gives you a lot of accuracy, but that is when and only when you have a lot of data that is available. Okay, so that is that about the first derivative. What about the second derivative? So for the second derivative, um, we are going to have um, the central difference formula. When do we use this? Okay, so of course it's still the same. This is preferred for interior points. What about the uh, 3 point second derivative? We use this at boundaries, similar to the previous part. Okay, so even the 5 point, okay, the 5 point second derivative, so like the midpoint, we also use it. It gives you a lot of accuracy, but you just have to ensure that you have a lot of data points. Okay, so that's the idea regarding uh, data symmetry under numerical differentiation. So just make sure to say you subscribe to the channel. There will be a lot of videos on this, particularly this. Yeah, so that's all in this one. Thank you very much for watching, and we'll catch you in the next one.